Sorry for the wall of text here, but I'm trying to throw all this information at you pretty quickly. Phases of matter, this is sometimes called states of matter. We're talking basically here solids, liquids, and gases. Solids, liquids, and gases. And I hope that you guys are already familiar with this idea um, that the particles in these types of substances, in these phases, are arranged differently. Now, what you may not know is that particles of matter tend to, this is not always true, but they tend to kind of stick together. They tend to be attracted to each other. So think about the particles in your desk right now. Your desk is made of billions and billions of particles, of atoms and molecules. Your desk is not melting all over the place. Those particles are not flying off randomly. There's something locking those particles together, keeping them very, very close together, keeping them locked into place so all they can do is kind of vibrate. So this might represent the particles in your table or the particles in a piece of ice. It's a solid. The particles are locked into place. There's something holding those particles there. What is it that is holding those particles in place? It's these attractive forces. It's the fact that these particles are stuck together. We call these intermolecular forces. Inter meaning between, molecular meaning the molecule. So in between the particle, in between my particles here, there are these weak attractive forces that are locking those particles in place. I'm diagramming in red right now. Weak attractive force is locking the particles in place. That's called an intermolecular force. You'll see here that I've also called it a Coulombic force. Does that ring any bells? It is a force that is governed by Coulomb's law. This is a little bit outside the scope of this unit, but these particles are made of atoms, and atoms are composed of charged particles. So it's an electrostatic force that is kind of sticking these particles together, keeping them locked into place. It is governed by Coulomb's law. We're not going to review that in depth right now. You guys have already done your quiz over that. But I do need you to know that these intermolecular forces are due to attractive forces between charged particles. So it all has to do with how much charge there is, how close together they are, things like that. So different substances have different types of intermolecular forces and different strengths of intermolecular forces. There are different forms of this force, different types of it, and those have different strengths. So anything that is a solid, look around you, look at some solids right now. Those solid substances are solids at room temperature because these intermolecular forces are strong and effective. Strong and effective intermolecular forces result in a solid substance. Solids are defined by the fact that they have a definite volume. The amount of space they take up cannot be easily changed, so they cannot be squished down and compressed. They kind of randomly expand and start taking up more space. And solids have a definite shape. Why is that true? Because the particles are locked together with these strong and effective intermolecular forces. If the intermolecular forces are just strong enough to hold the particles together, but weak enough to allow the particles to still flow over each other, then that is a liquid substance. So in order to get a liquid, we have to have intermolecular forces that, so forces between the particles that still kind of cohere, still kind of bring the particles together, but they're not quite strong enough to lock the particles in place. And the particles are allowed to still move and kind of flow and mix around and tumble over each other. So unlike a solid up here, the particles in a liquid, the intermolecular forces are a little bit weaker. The particles are still held together, but they're not held together so tightly that they're locked in place and all they can do is vibrate. They are allowed to tumble, to roll, to flow over each other. This is why you can pour liquids, why liquids are sometimes called fluids, because they flow. Liquids do have a definite volume still. It is very difficult to compress these liquids together to get the particles to move closer together. And liquids are not randomly going to expand on their own. But liquids have an indefinite shape. Unlike solids, the particles are not locked together. They can flow around, they can tumble over each other. Liquids will typically take the shape of their container right? If you pour water from one cup to the other cup, that water is going to flow around and it's going to take the shape of whatever container you pour it into. So why does this happen? It's all about these intermolecular forces. They're a little bit weaker than the solids. What about gases? Well, gases basically have no intermolecular forces. Their intermolecular forces are so weak and ineffective that the particles are not even held together at all. So if I'm representing a gas up here, these particles are just completely free. They've been liberated. They are able to fly apart from each other. Their kinetic energy has, I guess you could say, won. It has overcome the intermolecular forces. Intermolecular forces try to keep these particles together, but in gases that is not happening. The intermolecular forces are pretty much non-existent, so the particles are allowed to fly apart from each other. So gases are very interesting. Gases do not have a definite volume. You can compress a whole bunch of gas particles together to make them fit into a very tiny volume. Or if you allow gas particles they will expand. They will fill up whatever container they are in. So if your parent brings some pizza into the front door, pretty soon you're going to smell that pizza even from your room. That's because gas particles are going to expand to fill up the whole house. The gas particles carrying that pizza odor are going to fill up your house, basically. Solid particles, liquid particles cannot do that. They are kind of confined, held into place. Gas particles are free to go wherever because unlike solids and liquids, gas particles pretty much have no intermolecular forces. Here you can see a really simple little simulation of what we've been talking about. This represents a piece of solid neon. You can see that we're pretty close to absolute zero. It turns out that neon is really bad at sticking to other bits of neon. So you have to get the temperature incredibly low to get these particles to slow down enough um, to cohere together. And this represents a solid. A liquid, you can see that the temperature has been raised a little bit. We have melted the neon, and now if you look carefully, the particles, they're still kind of held together, but unlike the solid where the particles are locked into place, there's a clear pattern, they're just vibrating. The liquid, these particles are tumbling, they're rolling, they're flowing over each other, they're kind of splashing around. This is because the intermolecular forces are now a little bit weaker. We have increased the kinetic energy, the temperature. By increasing the kinetic energy of the temperature, we have therefore weakened or reduced the effectiveness of the intermolecular forces. If we were to keep doing that, if we were to keep heating this up, these particles would eventually all fly apart from each other and get liberated as a gas. So let's see if we can turn this thing into a gas. And right now, this is gaseous neon. You can see that the particles have nothing keeping them together. They're flying apart. The kinetic energy has won. The thermal content has kind of won and has broken apart the intermolecular forces, allowing the particles to fly apart as a gas. So solid, very strong and effective intermolecular forces. If we heat up the substance and kind of weaken those intermolecular forces because we have increased the motion of these particles, it will melt into a liquid. If we keep increasing the kinetic energy of the particles, they're going to completely and totally break the intermolecular forces holding them together, and now the particles fly apart and have nothing to keep them together. They're moving too rapidly, and so it is a gas. So what do these phases of matter have to do with energy? Remember, we're trying to model changes in energy. What exactly is happening energetically in terms of the phases when we go from one phase to another? Remember, our whole example was taking a solid substance and melting it into a liquid. So how can we talk about energy here? It turns out that the stronger the intermolecular forces in the system, the lower potential energy there is in that system. So I want you to think about this. We've been talking about thermal energy, the energy due to the motion of particles in the system. And now we're bringing up potential energy, which is energy due to the arrangement of particles in a system. It turns out that if you have a system like this, which represents, what phase of matter do you think this represents? That's a solid. Why? Because the particles have a patterned arrangement. They're locked into place. What am I drawing right now? These are the intermolecular forces locking those particles into place. And the particles are just vibrating. So due to that arrangement, this system has a certain amount of potential energy. And it turns out that the stronger the intermolecular forces, the more locked together and arranged, the more locked together and orderly and patterned the particles are, the lower the potential energy is in the system. So particles in a solid with strong and effective intermolecular forces have low amounts of potential energy. Guess what? We're going to call this energy phase energy, and we're going to represent solids with 1 bar of phase energy. Particles arranged on the other end of the spectrum as a gas, where there are pretty much no intermolecular forces, weak and ineffective intermolecular forces. What kind of potential energy, what kind of phase energy do you think we're going to model them as having? Very high amounts, so 4 bars of phase energy. Particles in a liquid are somewhere in between. They have medium amounts of this potential energy, so 2 bars of phase energy. So this potential energy, due to the arrangement of particles in a substance, is referred to as phase energy. It's all due to the intermolecular forces locking the particles into place. So now I think we can finally go start answering our question. The question was something like this: a piece of ice melts as it sits out on the countertop. So I think we said that we are going from solid water, ice, with strong and effective intermolecular forces, locking the particles into place so that they are only capable of vibrating. This would be my solid water. And we are taking it and we are changing it into a liquid. So the particles are still held together, but now they're held together more loosely, and the particles are capable of moving around more. They are able to roll and flow and tumble over each other like a liquid. Notice I was very careful in my diagram to keep the number of particles the same. I have 11 particles over here. I have 11 particles over here. Why do you think I did that? Well, in any change like this, all I've done is I've taken particles that are arranged in a solid, and now I have them arranged differently, arranged as a liquid, but I cannot destroy the total number of particles. So we did say that this was pretty simple. We know that we start with very cold ice, and we're going to end with something that's room temperature, so the thermal energy is increased, but we said that we have to talk about the phase. So let's think about this. The phase energy of a solid, do you remember what we said about that? Yeah, this is a type of potential energy due to the arrangement of particles in the substance, due to the effectiveness of the intermolecular force. So the intermolecular force here is very strong and effective, locking these particles into place, holding them in an orderly arrangement. That represents a low amount of potential energy, so the phase energy is low. In a liquid, the intermolecular forces have been weakened. Well, think about this. It's going to take some kind of energy to weaken those intermolecular forces and cause the particles to be more spread out, to kind of pull them apart. That is the potential phase energy that we are talking about here. So because the particles have a less orderly arrangement, they are more spread out, the intermolecular forces have been weakened. It takes energy to do that. That's potential energy. The potential energy of this system has increased. We use 2 bars to represent the phase energy for a liquid. So it begins as cold ice with low amounts of potential energy, and it ends with room temperature liquid with medium amounts of potential energy. I guess you could say 2 bars of this potential energy. And again, why are we talking about that potential energy? Because it's not enough. Here in this example where we have a change of phase from solid to liquid, it's not enough to just talk about the thermal energy. We have to see what's happening with the arrangement of the particles, with the potential energy of the particles.